The title is Two-Dimensional Easing Superconductivity in Gated MOS2. So MOS2 is a very popular two-dimensional material nowadays. So MO is this moly and S is the sulfide. So for this material, with a monolayer of moly disulfide, so what you have is it's a three-layer structure. So a single monolayer is composed of three layers. The top and the bottom layers are the sulfide atoms, and the middle layer formed in a triangular lattice, that is a moly atom. So, but for this material, if you look at it from the top, it seems like it's just like a graphene type honeycomb lattice structure. So this material, graphene is it has been a very popular material in the past decade. And what is interesting about this material is that there are two things. One is, you see, for graphene, all the atoms in the AB sublattice, they are just carbon, so you have this sublattice symmetry. But for this moly, if you look at it from the top, you find that there's no sublattice symmetry. So what does it mean? It means that you can easily actually open a gap. You break the sublattice symmetry, you can open a gap in graphene. So this material is a two-dimensional material and it's gapped. Second, for graphene, it's rather light, so the atomic spin-orbit coupling is weak. But for this material, moly, it can be very heavy. So in this material, you can have strong spin-orbit coupling, this will affect the property of this material a lot, especially the topological property, which we are going to talk about. So this spin-orbit coupling is very important. And third, there's another advantage about this material over graphene, which is the fact that it is superconducting. There has been a lot of prediction about superconducting graphene. Indeed, Yao did some very important work a few years back, and he predicted that if you have graphene, if you look at this graphene honeycomb lattice, you can ask yourself, if the graphene is superconducting, what kind of pairing it's going to get. So Professor Yao and colleagues proposed that you will have a D plus ID, a D-wave superconductor. So in this, but the thing is that for graphene, the intrinsic superconductivity has never been observed yet. So, but for this material, it is superconducting.
Okay.
So that is the third thing. If you want to study interesting superconducting phase, this is the material you want to go to. First, you have the honeycomb lattice, and second, you also have strong spin-orbit coupling. And intrinsically, it is superconducting. So, okay, I will explain maybe a little bit more about later what I mean intrinsically in superconducting. Okay, but this material, when you make it superconducting, actually you need to gate it. Okay, so you have to tune the chemical potential. So when you gate it to the superconducting regime, actually people realize that it's not just superconducting. What happens is it's a two-dimensional material, and you know that superconductivity can be easily cured by external magnetic field. But this material, if you try to apply in-plane magnetic field, you realize that this material, this is the magnetic field, y-axis is the magnetic field you need to cure the superconductivity. So this is HC2, which is upper critical field. So after this regime, basically, if you apply a magnetic field higher than that, your superconductivity is gone. But if your magnetic field is at a certain temperature, it's lower than this critical value, you still have superconductivity. What is amazing is that recently, my colleagues in Netherlands, so he measured this upper critical field, and he realized that this upper critical field, it can be even at rather high temperature. This is the highest magnetic field they can apply, which is about 37 Tesla. that's the highest magnetic field, static magnetic field one can apply in the lab. So they try the best, but you see that the superconductivity is almost untouched. If they can easily go up to, they can go to lower temperature, but they cannot go to higher field. So you don't have data here. But this material can survive, the superconductivity there can survive under an extremely high magnetic field. And the question is, why? So I will explain this a little bit later. So, which is related to the spin-orbit coupling of this system. So this is the one. And second, so this Ising superconductivity actually caused by a spin-orbit coupling. The electrons in this material, actually, the spins, they are pinned to the up and down direction because of spin-orbit coupling. It's very different from ordinary spin-orbit coupling, which pin the Rashbach spin-orbit coupling, for example. They will pin, if you have a 2D system, the spin of the electrons, actually, on the Fermi surface, they are pinned to the in-plane direction. The electrons, they move around, but the spins are pinned to the in-plane direction because of the spin-orbit coupling. But that is the Rashbach spin-orbit coupling. But for this material, the electron spins are pinned up and down because of the specific type of lattice structure. That is this, the lattice structure related to this moly disulfide. So it's related to this kind of honeycomb lattice, but with broken sublattice symmetry. So, but there are actually a whole class of materials like this. The whole class of this transition metal dichiralganoid, so this DMT material. So another material, indeed, which is even more well studied, that is the niobium diselenide. And people realize that they have the same effect. So actually we propose that. So we propose that, so we first, my colleagues in Netherlands, they did the experiment on this. And very soon we realized that this actually has to apply for a whole class of material. So my friend Mac in Penn State, so he did the experiment for this material as well. And then similar thing happened. So for this niobium diselenide, this upper critical field also is extremely high. It's of order of, it's also, it can survive under the largest possible magnetic field you can apply. So and we call this type of superconductor Ising superconductor. So Ising superconductor, because the electron spins are pinned up and down. Just up and down direction, no other directions. So, and one may ask, okay, this 2D material superconducting with strong spin-orbit coupling, you ask yourself, well, besides the fact that it can survive under a very high in-plane magnetic field, so we can ask, what can I do with it? So recently, we proposed actually, this Ising superconductor, if you can induce pairing even on a half metal wire. And this half metal wire, if you put it on this superconductor, this half metal wire, it will become a topological superconductor indeed. And this half metal wire will support Majorana fermions as the end states. And that is basically the story, that you have a new type of 2D material superconducting with strong spin-orbit coupling, and you can use them to make Majorana fermions. So that is basically what I want to talk more about. So, but before that, I will talk about some history, why this Majorana fermions are so important, and why this material can help to do that. So we come back to this this Italian physicist Majorana. So he found a real. So I think we in the audience, a lot of us are doing high energy physics. So this morning we have this Higgs boson, and so in high energy, Higgs boson is the it's actually the topic right now. It's the most important issue that people are studying. So in condensed matter, we are also searching for a new type of particle, and that is Majorana fermions. So Majorana fermion, they have this. Okay, in high energy, they are the real solution of the Dirac equation. So in this, in condensed matter context, so the Majorana have this self-emission property, which is this gamma dagger equals to gamma. So the particle itself is also the antiparticle is actually the particle itself. So so in condensed matter physics, actually it's impossible to find them. So because of the self-emission property, it has only half the degrees of freedom of a usual fermion. So indeed, two Majorana fermions, they form a single fermionic state. So, for example, if you have two Majorana fermions, one localized here and another localized here, and these two Majorana fermions, they will form a fermionic state. And this fermionic state, they can, because it's a single fermion, and this fermionic state, it can be empty state, or it can be a occupied state. So, first of all, these two Majorana, they can form a local fermion. You see that the wave function, they can be separated very far apart from each other. And second, they can form a qubit, because you can have an occupied state and an unoccupied state. So Professor Xu must be very familiar with this kind of quantum qubit. So, and what is really interesting is that if you have two Majorana, for example, now they form an empty state, and you have another two Majorana, they form another empty state. So, and you can do braiding. Usually, you know that in quantum mechanics, when you do braiding, if you braid two bosonic, two bosons, your wave function, the total wave function will not do anything. If you have two, you braid two fermion, and your total wave function will acquire a phase, which is 2 pi. If it's exchange, it's pi. But if you do a full braiding, that's 2 pi too. So, but what I want to say is that usually, if you have a few particles and you just exchange the positions, you will not change your wave function. So even for anyons, in some laughing quantum Hall states, you braid the particles. What it gives you is it's the same quantum state. You may have a non-trivial phase, but it's still a trivial phase. It's still the same quantum state. But if you have a few Majorana, you do the braiding, you find that your quantum state can be changed from a state like this to other states. And immediately you see that, well, what is important is that you see this wave function is orthogonal to the original one, at least this part. So it's really a different wave function now. So, and this is called the non-abelian property of Majorana. This is a very exotic property, and so that's why, I mean, it's a very this attracts a lot of attention. So, and you can also use this possibly for quantum computation. So that's a huge effort in condensed matter physics to try to find this kind of particles.
And what's braiding in the physical world?
Braiding, for example, you just it depends on where they live. For example, you have these guys, they can live in the vortices of superconductors. Braiding meaning you exchange the positions of the vortices.
How do you realize it?
Realize what?
How to realize the operation.
Well, okay. So there are many schemes of doing that. Okay, one possibility. Well, can you jack the vortex around? That's very difficult. But actually, for some structures, which I may explain just in the next one. Actually, you have some you can do some 1D structure actually, and then you form some sort of T junction, and then underneath it you can gate. You can do some gating, So you can change the local chemical potential of your structure. And by doing this, actually, gating can change the position of this Majorana fermion. So they can move. They can, like parking a car. So for example, at a T junction, you can move this Majorana from here and then to this position, and then you move this one to here, and then you move this one back. That is an exchange.
So by the time series, different time, how do you correlate it?
No, it's a different time. So after the braiding, so you do it almost adiabatically. So you do it very slowly when you do the braiding. And after that, even though you do it slowly, what's interesting is that you get a different quantum state.
Yeah, I understand
Yeah.
different quantum state, but how do you correlate this first one? The first state that you create has to disappear from the system.
Oh, yes. So that is about the measurement. So the measurement is, for example, for this one, it is a quantum state, right? So if you have it forms a fermionic state in which it is empty. But you need to seek for properties, a different system is different. So you need to seek for property where this one, for example, now I have half of the probability after the braiding. Actually, these guys, originally it was empty, but now it's a field. So that's a field. Of course, the physical property can change when you go from an empty state to a fielded state, and that can be measured. So, and so now we come to, okay, you can say, where can I find this Majorana? And one possibility is, actually that was proposed in the year 2000, that if you have a P-wave superconductor, it's a P plus IP. Up to now, there's still no experimental realization of this. So for this type of superconductor, it's rather special that, okay, so first of all, it's unlike traditional superconductor in which you know that for usual S-wave superconductor, you have the electrons, they form Cooper pairs. With spin up and spin down, they form a spin single. So that means that in your system, you need both spin up and spin down electrons. But for this type of a superconductor, you write down your Hamiltonian. All you need, actually, you suppose your system is all the electrons are spin polarized. So spin polarized, you have only, say, spin up electrons. And then you pair these type of spin up electrons, they form pairs. So you see that, so this is just a, I don't have the spin label, it's just a spin up or spin up for example. And then they have some pairing. It's not a singular pairing, it's a triplet pairing. So, and then you find that with this kind of superconductor at the right regime, with a right chemical potential, and then you have actually Majorana fermion. If you create a vortex in this superconductor, you have a localized Majorana at the vortex core. So, but the key is that you need a you need actually only one. You can only have, for example, spin up electrons. In this system, you cannot have spin down electrons. You're allowed to have only one species of electrons. So not spin up and down. You can have only spin up or spin down. So that is required for you to make this P-wave superconductor. And of course, you can do this in 1D, which is you make this narrower and narrower and narrower. Actually. So and then your Majorana actually you have Majorana staying at the ends of the 1D wire. So this is a proposal by Kita in the year 2001. So these are the P-wave superconductors. But in reality, it's extremely difficult. Actually, we don't, after a long time of more than 15 years now, and we still don't have a solid example of this type of E plus IP superconductor. However, there's a breakthrough actually in the year 2008. So that is from a proposal by Fu and King. You know that King is the is the one who invented topological insulator. So for a topological insulator, you have the valence band and the conduction band. So it's an insulator. Your chemical potential is in between this is a band gap, and you have the chemical potential in between the gap. So, but for a topological insulator, what happens is that you have surface states connecting the valence band with the valence band with the conduction band. You connect them, and these states, if you look at the wave function, they are actually localized at the surface of the topological insulator. So, but what is very interesting is that there are two important things about this topological insulator. First, on the surface, these states on a single surface, on a single surface, these states are not degenerate. It's non-degenerate. You have a completely degenerate partner at the other side of the surface. But on one side, it's non-degenerate. So what does it mean? Now, if I put a superconductor on top, and put an ordinary S-wave superconductor on top. So here, for the surface state here, you have the spin-up particle. Here, you have the spin-down particle, but it's non-degenerate. Now, even though you have spin-up and spin-down, but for a fixed momentum, you don't have spin-up and down. There's no up and down. It's just, this is up, and here is down. It's non-degenerate. It's different from an ordinary. If I give you the band structure of some ordinary time reversal invariant material, and usually you have the spin up and down together. Okay, at each K point, you have both spin up and spin down. It's degenerate. But for this material, it's non-degenerate. It happens only at the surface. Okay, so with that, and also, you have spin up and down. Now, this is spin up and spin down. So, it's actually compatible with superconductivity. Because ordinary superconductivity prefers to pair electron with spin up as a positive momentum and spin down electron with negative momentum, with opposite momentum. That's what ordinary S-wave superconductor tries to do. That's what they want to do. And this material, it's actually possible using just S-wave superconductor to pair the electrons at positive K and the negative K with opposite spin. So, indeed, you're looking at if you write down the Hamiltonian of this superconductor with the surface state, you actually find that the Hamiltonian can be mapped to this one. It's indeed, so they can map to each other. So what does it mean? It means that you have an S-wave superconductor, but if you put an S-wave topological insulator, you can make a topological superconductor, actually, which support Majorana. If you create a vortex, you will have a Majorana inside, in the vortex. So that's a very important. Actually, you will see. If you look at the literature, there are lots of people, even now, in recent years, a lot of people are trying to search Majorana fermions in this system. So there's another system which is related to spin-orbit coupling, and people also propose that if you have a wire with strong spin-orbit coupling. So what happens is that the spin-orbit coupling, if I don't have spin-orbit coupling, what you have is just a parabolic band. This is the K, this is the energy. So what you have is just a parabolic band. But if once you add spin-orbit coupling, the spin-orbit coupling will actually split. Will split your band into the degenerate band into something like this. So, and what is interesting is that now, so this is okay, but now if I apply a magnetic field, the magnetic field, so before you have this band and you have a crossing here, this crossing is actually protected by time reversal symmetry. But once you break time reversal symmetry, you can open a gap here. Once you open a gap here, you realize that I can tune my chemical potential here. Once I tune my chemical potential here, I will. You see that now? Also, there are only 2 Fermi points at my Fermi energy. 2 Fermi points is if it's a 1D. If it's 2D, it's just one Fermi surface. So this is very much like this case. In the topological insulator case, you have just one spin up state here and one spin down state here. So for this material, it's the same. Now, because the middle band is gone, so I have only a spin up state here and a spin down state here. So you find that now I put this material, so I have the spin orbit coupling. The spin orbit coupling will shift my states, and then I apply a magnetic field that opens the gap. Now I put it next to a S-ray superconductor, induce a pairing between the state here, the electron here and the electron here, and then you have a topological superconductor. So in this case, you have two Majorana fermions sitting at the ends of the wire. But that is how you create a topological superconductor. So actually there are lots of, but there are still some problems. So a few years back, so we just asked this question: if you have Majorana here, how can you detect it? So you detect it by tunneling. If you have a Majorana fermion here, this Majorana actually, they are at 0 energy. They are pinned at the Fermi energy actually. So and then you can do a tunneling. So you can put a lead next to your end, and then you try to shoot electrons in. And if you have a state there at 0 energy, so you have a 0 energy, you actually what you expect is you have a 0 bias conductance peak. So that's what you do. You have this. What you predict is that you have this voltage. That is the voltage difference between your STM tube and your wire. And this is the IDV, which is the conductance. You can measure the tunneling conductance. And you would expect there's a conductance peak at 0 energy. This is partly due to the increase of the density of states at 0 energy. But there are some other reasons. Especially that it's not just the density of states, but also we predicted that at 0 temperature, this peak, this 0 bias peak is the IDV. The peak is 2e squared over h. So it's quantized. The 0 bias peak is actually quantized. So when you do the tunneling measurement, you see that you have a 0 bias peak, which is a quantized. Of course, at finite temperature, the peak should be lower. So a few years after the prediction, there was an experiment by again a Netherlands group at Delft. So, and they do the measurement. They look at this material. This is the wire. That is the wire here. Schematically, this represents the wire. And there's an S. The S-wave superconductor represents the superconductor here. They apply a magnetic field. So that's the magnetic field here. So in principle, you can create Majorana when you have magnetic field. So, and then they look at it. So without magnetic field, this line, the bottom line is 0 magnetic field. So there's no 0 bias peak, there's no peak in the conductance. You see, actually it's a dip. But when they apply the magnetic field higher and higher and higher, actually there's a conductance peak. The IDV peak appear at 0 bias. So, and it's possible that this can be Majorana, but it's also possible that it's not. There's a lot of argument about this. For example, we studied this problem right after they published the experimental result. we argue that this peak can actually maybe have some disorder origin. So it's very hard to tell just from this. It's a real Majorana or not. So there's a lot of debate about this. So charge transport is it's very difficult to tell. And recently we also have a proposal about the spin signature of Majorana. Basically, last year we predicted that. So if you have an ordinary superconductor, so I have a normal lead, I try to shoot electrons in. These electrons, they have to form pairs inside the superconductor. So I shoot a spin-up electron in, and then below the Fermi energy, I have to grab the electron with opposite spin, the spin-down electron. And this spin up and spin down electron tunnel together into the superconductor and form a Cooper pair. So, and this is a spin singlet Cooper pair. This is for ordinary superconductor. This process is called the Andrew reflection. Okay. So, but what happens for a topological superconductor is very different. You have the Majorana sitting here, or somehow you have the Majorana here. When you shoot the electron in, a spin-up electron in, actually, what you have to do is that this spin-up electron will partner with a spin-up electron below the Fermi energy. It's not spin down. For ordinary superconductor, it's spin down. But for this topological superconductor, it has to be spin up. Spin up electron in. It grabs a partner, which is also spin up, and then both of them. Oops. Oh, sorry. This should be spin up. This wrong in the picture. So actually, and then they form a spin up pairs. Indeed.
This is pure superconductor.
Yes, that's a very good question. I actually cannot say this picture is wrong. It actually took me a long time to think, should I draw it this way or this way? Because this system, you have spin-orbit coupling. Spin is not conserved. What happens is that at the beginning, when you tunnel electrons in, at the interface, it is both spin-up electrons tunneling in. So here you have no problem, and then after this tunneling, you tunnel a pair of spin-up electrons in, but you have spin-orbit coupling in your superconductor, and it is S-wave. S-wave. So eventually it has to relax back to this structure. So let me see if I should have okay. We explained this in more detail, actually in the archive work we put on last month. But what I want to say is that here you look at the pairing near the interface when you have the Majorana. The pairing is spin triplet pairing. The electron they pair is up and up, down and down. Okay, up down it depends on the magnetic field and things like that. But it is just in a certain direction. But once you go into the bulk, it is a spin singlet pairing actually. So this is a you can calculate the pairing correlation, and you really realize that on the near the place where you have Majorana is triplet, and then you go into the bulk is singlet. So
there actually be a process for spin flipping.
Yeah, inside the superconductor, yes, because you have spin-orbit coupling. Your spin is not conserved. That's very important. So, and it's more than just equal spin. And actually, we call it a selective equal spin, because your Majorana will actually select. I have spin-up electrons coming in, you can tunnel. But your Majorana will tell you, if you have spin-down electrons coming in, sorry, you cannot tunnel. You just bounce back as like hitting the wall. The electron, spin-up electron will go through. The spin-down electron will just get bounced back. So this is a very special property. It is for Majorana. So we show it's due to this have self-emission property of the Majorana. So what does it mean? It means that I have a normal lead with both spin up and spin down electrons coming in. But only spin up electrons can go through. Spin down electrons will all bounce back. So the current going through is actually spin polarized. Even though your lead is not spin polarized. But the current is spin polarized.
It's a spin filter.
It's a spin filter, actually. It is a spin filter. So, but what is more interesting is that
What's the priority of the Majorana spin?
so the direction of the spin, you mean, right? That is determined by the details. For example, the direction of the magnetic field you apply, and also your system itself has a spin-orbit coupling. Spin-orbit coupling in a wire, it acts like an effective magnetic field actually. So it is really the combination of the two that will roughly determine the spin polarization of your Majorana form, of the spin current. Yeah. So I can explain a bit here as well. So, but as you know, if I have a single Majorana at zero energy, when I shoot electrons in, the conductance here is actually you have a maximum value, the quantum conductance. 2e squared over h, that's the maximum you can get. That's the maximum value, maximum conductance you can have. But you may ask the question, can I obtain a very high spin polarized current? So with very low resistance and very high conductance, can I do that? So the answer is actually yes. And then you need to go to you need to go to a not ordinary topological superconductor, but you have to find a superconductor which is nodal, it's gapless in the bulk. You have to find a superconductor, a topological superconductor, not just an ordinary superconductor, but it's nodal in the bulk. It's like a D wave. D wave is nodal, but D wave is not topological. But we need to find a nodal superconductor which is also topological. And you can do that. And so we have a model, and I will not explain too much about this model. But I want to give you the energy spectrum of. So basically what you have is again, it's not a Rorschach quantum well, but you have a so-called Jesselhaus quantum well. So it's a quantum well made of semiconductors, and you have spin-orbit coupling in the system, and you put it next to a superconductor. So you make it superconducting. You need to apply an in-plane field. So by doing this, the energy spectrum of this setup, this superconductor, it will look like this. This is the pairing gap inherited from your S-wave superconductor. But what you find is that you have, instead of gapping out the whole thing, you have actually nodal points. And these nodal points, just like the nodal points in D-wave superconductor, and they are connected by a flat band. This is a flat band. It means that it's a very large density of state, just like on the edge of a D-wave superconductor, at one of the edges, the 110 edge, you have a large number of zero energy states, but they are not Majorana, they're just ordinary fermions. But for this material, you can have a large number of Majoranas sitting at the edge. So I denoted the red here. It's a whole band of Majorana fermions. And all this large number of Majorana fermion, if you put a lead next to it, you can also induce spin polarized current. But because now you have a very large number of Majorana fermion, so actually the spin current you can obtain is actually huge. It just yes.
So just look at the Hamiltonian.
Yes.
The second line.
Yes.
Sine kx.
Yes.
What is that?
This is the spin orbit coupling term. That means that the k is the momentum. This sigma z is the spin. So your momentum coupled to the spin. If for electrons with opposite momentum, it will experience an opposite magnetic field.
Why sign?
Oh, sign is just from a time binding model. It just you do a small k expansion. It's actually k. It's just k. This Hamiltonian is valid for small k, so you can just treat it as k. So this is the momentum quantum number coupled with the spin index. So this is just like the magnetic field. For example, the magnetic field here, if I apply a magnetic field in the y direction, so what does it mean? I will flip the spin. The spin, I will align the spin, the sigma y, in the y direction. Right? But of course, the external field you apply is a constant. It's just a constant By. But here, it is not the magnetic field you apply. It is the momentum which coupled to the spin. So for electrons at different momentum, you experience different spin. The larger the momentum is, the larger the spin. It's very interesting actually. But of course, you have the Fermi energy pinned in. So this roughly is the Fermi energy, Fermi kF. Yes. So this is a very interesting thing about the spin-orbit coupling. This is also the reason that why the electronic bands can be split. This is why they can be split. They are split because of you basically have a magnetic field applied to it. So the spin up and spin down states are not degenerate anymore. Are not degenerate anymore. Time? Okay, how much time can I have? Up?
Okay.
Oh, okay. Sorry. Maybe I have 2 minutes?
Yeah.
Oh, but I explained the main points already. So, but there are lots of problems in finding Majorana. But okay, first of all, just 2 minutes. First, you get this MOS, so you can also find Majorana. Okay, but you need for this guy, I look at this MOS to the band structure. You find that if you look at it closely, you find that the bands are actually split. Very much like the Rashba case. But they are split by spin-orbit coupling. So you actually, this guy itself is superconducting. So, but you can make it actually a topological superconductor. We kind of calculated the phase down and find that you can have a topological superconductor there. But you can even ask this question. Even though this guy is not topological, if I have, just like I'm in ordinary phase, so for example, I'm just now I have strong spin-orbit coupling in the material, but I just have S-wave superconductor. Is there any interesting thing that can happen? And the thing is that this I explained, this guy can survive under extremely high magnetic field. The reason is the following. The reason is that the spin-orbit coupling you have is a very special type. Here are the pockets of the Fermi surfaces. You find that because of spin-orbit coupling you have, at this pocket, it's a spin down. So you have an effective magnetic field which points down. But in this pocket, because it's spin-orbit coupling, the electrons experience opposite magnetic field, and that is up. So because of this internal pinning of the spin up and down, it's very hard for you to have an in-plane field to cue it, because they are already pinned by the spin-orbit coupling. And you calculate that, you find, so that is our theoretical fitting to the data. It's basically a perfect fit. So you take into account in this system, because of gating, you have Rashba. You need to take into account the Rashba, and you also need to take into account the intrinsic spin-orbit coupling, and then you can fit this data perfectly, and you can extract the spin-orbit coupling strength of the material. And after doing that, this is the data for the for niobium diselenite also. You see a huge increase in the upper critical field, but not the out of plane field. The out of plane field, you can easily cue it, just like this. Only the in-plane field is very, in-plane upper field is very, very high. And so we also propose that we calculate, okay, with that type of spin-orbit coupling, all you need is put a half metal wire on top of your TMD material, and you will have Majorana fermions sitting around. Okay, that's all. Thank you.
very good.
非常好，因为刚才已经提了很多问题了，那么现在时间关系，我们再提一个问题，有没有？
我们会再好，谢谢。
就是那个稳定性的话，你是由什么来保护的？就是说不会碰到那个是由磁场来，还是那个 gap？
哪一个稳定性 ？Majorana 的。
我说你的 IC superconductor 的
Oh
稳定性。
Oh, that it's just from the band structure. It's a huge energy scale actually. It depends on if MOS2 in the conduction band is about 10 MeV. So that is still a small scale. But if you look at the band structure, it's a small scale, 10 MeV.
Yeah.
But if you look at superconducting scale, it's huge. Your pairing, I mean the pairing energy scale is 1 MeV.
Yeah, that means the TC is very high.
This material, it's actually can rather high, it's almost 10K. It depends on the gating. Yeah, it can go up to like 10K.
Very good.
Thank you. It's very robust. Yeah.
我们感谢那个 Professor 和
Thank you.
精彩的报道。